Hello and welcome to Chapter 4, where we are going to learn about present worth analysis. So in this lesson, we are going to learn how to compare alternatives using a present worth basis. So in order to do that, we must first learn how to formulate alternatives, and then we will apply present worth analysis on single, equal life, and different life alternatives. So let's begin. Here's a brief recap on the common terms and symbols that are used in our cash flow diagrams. So P stands for present worth or present value of money at time t equals 0. F is the future worth or future value of money at a future time. And A, which stands for annuity, is a series of equal and periodic cash flows, and the unit is currency per period. So first, we must understand the reason of doing present worth analysis. So present worth analysis is a method to compare and evaluate alternatives based on the present worth of money. So you can use present worth analysis to evaluate a single alternative and determine if it is economically viable. And you can also apply present worth analysis to compare multiple alternatives and select the most economical one. So in a present worth analysis, the future cash flows of all alternatives are converted into a present worth value, which is then compared. Now let's look at an example of applying present worth analysis to evaluate a single alternative. So let's say you know how to make delicious nasi lemak and you plan to set up a home business selling nasi lemak. So the cash flow diagram of your proposed business could look something like this. So initially you have a first cost to purchase the equipments for your business, and then you have annual operating costs, and you have the projected annual revenue, and let's say you plan to close down and resell the business in year 4. So by applying present worth analysis, you can determine if this proposed business is economically justified and if it can meet a certain target rate of return, I. So in the present worth analysis, all these cash flows are converted into a present worth value at a certain target rate of return. And if the present worth value is bigger than 0, then the proposed business is economically justified and it can meet the return rate, the target return rate. However, if the present worth value is less than 0, then the business will not meet the target rate of return and therefore it is not economically justified. Present worth analysis is also used to compare multiple alternatives. So in this example, you have two different projects with two different cash flows. So by applying present worth analysis, the cash flows for each alternative is converted into its present worth value, which then becomes the basis for comparison. So here is an example of applying present worth analysis to compare multiple alternatives. So the first alternative has a first cost of $2,500 and an annual operating cost of $900. And the second alternative has a first cost of $6,000 and an annual operating cost of just $50. So as you can see, the comparison is not straightforward because even though the solar powered equipment has a more expensive first cost, but its annual operating cost of $50 is much cheaper than the annual operating cost of the electric powered equipment, which is $900. So by using present worth analysis, we can arrive at a fair basis for comparison. We can convert all these different cash flows into a present worth value, which then becomes the basis for comparison and for selecting the most economical alternative. Before an alternative can be analyzed or compared with the present worth analysis, it must first have some cash flow estimates. And these cash flow estimates include its first cost or its initial investment and its expected useful life, as well as its resale value at the end of its useful life, and the costs that are needed to maintain the alternative, which can include the annual operating costs as well as the maintenance and operating costs. Now let's look at the steps to apply present worth analysis on a single alternative. Now the first step is to calculate the present worth value of that alternative at a stated MAR. In the second step, if the present worth value of the alternative is bigger than 0, then the alternative is economically justified. Conversely, if the present worth value is less than 0, then the alternative is not economically justified. Now let's try this exercise to apply present worth analysis on a single alternative. In this example, we want to determine if this project is economically justified. So the project has a first cost of $2,500 and it has annual costs of $900 per year. It also has a projected annual revenue of $2,000 per year, and at the end of its 5-year lifetime, it has a salvage value of $200. Interest rate is at 10% per year. So in this present worth analysis, we will convert all these cash flows into present worth value at T0 and see if it's bigger than 0. So let me explain what's happening here. The first term is the first cost of the project, and since the first cost of the project is already a present worth value at T0, so you don't need to do any conversion here. In the second term, I'm taking the net cash flow between revenue and the cost. And since these cash flows that occur between year 1 until year 5 is a uniform series, so I need to convert them into present worth value using the P given A conversion factor. In the third term, I'm converting the salvage value of the project, which is a future worth value, to present worth value at T0. So that's why I'm using the P given F conversion factor. Now let's plug in the values using the formulas. So if you do the calculations, you will find that the present worth value of this project is equal to $1,795. So what we have found is that the present worth value of this project is equal to $1,795 at the interest rate of 10% per year. So since the present worth value of this project is bigger than 0, so therefore this project is economically justified. Now here is a very interesting example of applying present worth analysis to evaluate a bond investment. Now some backgrounds. A bond is an IOU that is issued by corporations and governments to raise capital. So when you buy a government bond, you are lending your money to the government, and in return, the government will pay periodic payments of interest until the maturity of the bond. So the face value is the value of the bond, and it is this value that is returned to you at the end of the bond's life. Now let's apply present worth analysis to evaluate the bond investment in this example. The investor is asking if this bond can make 7% per year. So the cash flow diagram for this bond looks like this. The first cost of the bond is $9,500, which is the face value of the bond that is discounted at 5%. At the end of the lifetime of the bond, the full face value of the bond of $10,000 will be returned to the investor. Now the lifetime of the bond is 10 years and the interest on the bond is paid semi-annually, that means twice a year. So therefore we have a total period of 20 in this cash flow diagram. And in each period, an interest amount of $300 is paid, making the total interest paid per year is $600. So coming back to the question, will this bond make 7% per year compounded semi-annually? So to apply the present worth analysis on this bond, we convert all these cash flows into the present worth value at T0. The interest rate I in our calculation should be 3.5% because the 7% rate per year is compounded semi-annually. And the total period N is 20 periods. So in this calculation here, you see that the first term here is the present worth value of the first cost of $9,500. The next term is the future value of the face value of the bond, which is $10,000, which is converted to a present worth value over 20 periods at 3.5%. And in the last term here, the interest payment of $300 every 6 months for 20 periods is converted into the present worth value. And we find that the present worth value at interest rate of 3.5% per 6 months basis is minus $210.62. So because the present worth value is less than 0, the bond will not make the targeted rate of return of 7% per year. Now let's discuss how to apply present worth analysis to compare multiple alternatives that have equal life. So to compare equal life alternatives, the present worth value of each alternative is calculated at MAR, and then the alternative with the numerically largest or the most positive present worth value is selected. So in the following examples, we have the present worth values of two different alternatives. In the first example, the present worth value of the first alternative is negative 1,500 and the present worth value of the second alternative is negative 500. So in this case, the second alternative is selected because the present worth value of the second alternative is numerically larger than the present worth value of the first alternative. In other words, the present worth value of the second alternative is more positive than the present worth value of the first alternative. Another way of looking at this is that by choosing the second alternative, we lose less money because the present worth value of the second alternative is just minus $500 compared to the present worth value of the first alternative, which is negative $1,500. And finally, in the third line here, the present worth value of the first alternative is $2,500 and the present worth value of the second alternative is $1,500. So therefore, alternative number 1 should be selected because its present worth value is more positive than the present worth value of the second alternative. In this example, we want to compare two different alternatives using the present worth analysis. We are given two different options for two different water heating installations. The first option is the electric powered installation, which has these cash flows. And the second option is the solar powered installation, which has these cash flows. Using present worth analysis, we want to determine which of these options is more economical. And we want to do this analysis at the given MAR of 10% per year. So what we are going to do is we will convert the cash flows for each alternative into present worth value, and then we are going to compare the present worth values and make our decision. So let's start by finding the present worth value of the electric powered installation. So the first term here is the first cost of the electric powered installation. The second term here is the annual operating cost of the electric powered installation. And the third term is the salvage value of the installation. So plugging in the values, we find that the present worth value of the electric powered installation is equal to negative $5,788. Now let's proceed to find the present worth value of the solar powered installation. Alright, so we find that the present worth value of the solar powered installation is equal to negative $6,127. Then we compare the present worth values of both alternatives, and we find that the present worth value of the electric powered installation is more positive than the present worth value of the solar powered installation. So therefore, present worth value of the electric powered installation is bigger than the present worth value of the solar powered. So therefore, we choose the electric powered installation. Another way of looking at this result is that by choosing the electric system, we spend less money compared to the solar powered installation. If we choose electric powered installation, we only need to spend about $5,000. But if we choose the solar powered installation, we need to spend about $6,000. So therefore, we choose the electric powered installation based on the present worth values. Sometimes the alternatives that you want to compare using the present worth analysis do not have equal life. So there are two methods that you can use to apply present worth analysis on alternatives that have different life. The first method is by using a common study period that is fixed for all alternatives. The second method is by using the least common multiple of the alternatives' lives. However, the study period method is recommended over the least common multiple method. So in order to use the method number 1, we have to apply the same length of study period N for each alternative. So if the alternative has a lifetime that is bigger than N, we use the value estimate for the salvage value at year N. If the lifetime of the alternative is less than n, then we estimate the costs for remaining years up until year n. And all cash flows that are outside of the study period are ignored. In method number 2, the least common multiple of the alternative's lives must be determined, and this could be unrealistic at times. For example, the least common multiple of 5 years and 9 years is 45 years. So applying the present worth analysis using the least common multiple method is rather complicated because the analysis must be applied for multiple life cycles. Now let us look at an example of applying present worth analysis on different life alternatives. So we have two locations here, and each location has a different lifetime. Location A has a lifetime of 6 years, while location B has a lifetime of 9 years. And we want to apply present worth analysis to select the lower cost alternative. And we want to use two methods to apply the present worth analysis. The first method is by using a 5-year study period, and the second method is by using the LCM. So in the first method, we fix the lifetime for both alternatives to 5 years because the study period of our analysis is 5 years. In addition, we assume that the deposits are still returned after 5 years. So the deposit return for location A is 1,000 and for location B is 2,000, and these are returned after 5 years. And these are stated here in the future worth values for each location. So we then convert the cash flows for each alternative into the present worth value at the stated MAR of 15% for 5 years. And we find that location A should be selected because the present worth value of location A is more positive than the present worth value of location B. Now in the second method, we want to apply present worth analysis using LCM or least common multiple. Now location A has a lifetime of 6 years and location B has a lifetime of 9 years. That makes the LCM is 18 years. Which means that location A has to be repurchased twice at years 6 and 12, and location B has to be repurchased once at year 9. And in using this method, we assume that all cash flow estimates are repeated over the multiple life cycles. So these are the cash flow diagrams of the alternatives over multiple life cycles. So as you can see, location A, the lifetime of location A is repeated twice, and the lifetime of location B is repeated once. So this altogether makes the total number of periods for the present worth analysis equals to 18 years. So we then convert all these cash flows over multiple life cycles into a present worth value at T0, and we find that location B should be selected because the present worth value of location B is more positive than the present worth value of location A. And please note that the present worth analysis using LCM method gives you a different result from using the 5-year study period method that we discussed earlier. So we have arrived at the end of the lesson. Thank you for watching. These are the problems that you can try for chapter 4.